record. Alrighty, now I will screen share while waiting for other folks to come in. Well, you survived, almost 2 classes counting today. Oh, this is when you guys give a thumbs down to say, oh, no. This is one of the hardest classes I've ever had. It can't end. It's so fun. Oh, Antonio's here. So, tonight, as we're waiting for Master X in, so we have our usual questions, answers, and general questions. Then we'll go with the homework and our really cool PowerPoints. And don't forget you have an article assignment due this week. Identical type of thing done the first one. We'll talk about that again. Breakout groups, and then an extra credit option. Oops, got to add Jordan and Ryan. Jordan and Ryan. Where'd you go, Ryan? You're on this here somewhere. There you are at the bottom. Okay, so 13. We're only missing 1, 2, 3 people. Won't they be sad? We won't tell them about the extra credit. It'll be our secret. If you don't come tonight, you have to count on someone else telling you about it. So, before I go on, anyone have any general questions about stuff? Not about specific assignment questions, but general, what do you want to know or hear about or care about or anything in that regard? Hearing none. Cool. Then I'll move on. Oh.
I have one quick question.
What do you got?
Is that our quiz, is that next week or this week?
The quiz 2, you mean? Yeah. That is, if you, we'll scroll over to share my screen. And if you look, quiz 2 is actually
Finals
week. Same format as the last one. I think there's like fewer questions. There's like 15 questions. I'll talk about it next week in detail, but it's going to be the same format, only on the last 5 chapters instead of the first 5. But it's actually your final is that quiz 2. Otherwise, it's going to be exactly format-wise, except for different chapters and the same and different. Let's see, anything else to fewer questions because we didn't have as much definitional stuff. But yeah, that's finals week out there on March 15th. Same time, same place. So first day in finals week, you get to take mine first. And we'll talk about that in detail next week, but that's next week. Oh, and Bradley's here. Hold on, where'd you go? Or Braden, not Bradley, Braden. Bradley's my other class. So now we're just missing Jacob. Doesn't he know what he's missing? Okay. So, I'll pull that back over. Now then, tonight's homework. Theta. So we'll come back to chapter, that's chapter 8. That was exciting. Chapter 8 was an interesting setup. Let's go to homework theta, and I will pull it over so everyone else can see it. Now, I did mine a lot more elaborately than everyone else might have because I did mine multiple ways and in great detail. I've done my first run through on people's homework, still have to do another one. So any comments you see on your homework so far that we'll put in there today, don't pay them any attention until I post the grades because I may change them. So 8-2, and this is all about choices and different rates and net present value and when rates fit in and don't fit in to make your projects or multiple projects good, bad, or indifferent. So this is what we did in class. And so everybody should have had it all done perfectly. All these keep saying that says construct a choice table for interest rates from 0 to 100%. Again, if you didn't do it to 100%, I mean, on this particular one, it was fairly easy to say just after about 20%, everything was 0 forever. So if you didn't do it the full 100, basically 100 is their standard way of saying students, when you just set an interest rate table, people would say, how much do we have to do? And a few years ago, actually, when the professor who wrote the textbook started adding that anecdote, like on the 12th edition, 0 to 100. We all got asked that so often, he said, fine, I'll make them do it to 100 just to be mean. I don't know, but. So you had 2 options, if you will, by Y or by X. And the whole point of this was to get you to figure out, when things we crossover and to do essentially those net present value by rate tables. because this chapter basically is in the things of saying when you don't know for sure what your rates are, how do you determine what it is viable over different rate times? And that's when we sort of combine our net present value and internal rate of return for different objects. So in order to figure out this, and you have this chart here where let's zoom to selection, where I graphed the net present value, and I only did 25 because I thought once everything's zero, why bother? And you can't read this if you did it 0 to 100. Then the lines get too small. And you see that at a certain time, if you got net present value going up and down the side and different rates, interest rates along the vertical, or excuse me, horizontal, well, at one point, Y is more profitable, then it crosses over to a point, and then X is more profitable up to a point where they both are below zero. And you can tell that X basically stays profitable longer, meaning above zero, than Y, even though Y starts off being more profitable than both. Okay, there's a couple of ways you can do it. And so far, the one thing that people are losing points for the most, and it's one of those, as my dear partner Dad would say, if all else fails, answer the question, is that you actually came up with really nice calculations, but didn't say anything about them. Because the choice table, if you look like the examples in the book, or like I do, whether you did a choice table like this, or like I do, highlight green parts and say this is acceptable up to this point. If you just put a bunch of numbers up there and don't say anything, there's no recommendation, and there's essentially no analysis, if you will. Analysis is looking at the numbers you create. A lot of people lost points because you had beautiful numbers up here, but you didn't actually say anything about them. And it was really frustrating because it's like, oh, you obviously showed you can do the calculations, but you didn't go back and actually answer the question. Now, at this point, they say, okay, construct a choice table. So what I did, whether you did it in a chart like this and calculated, different rates of return, or just did it here where I calculated the internal rate of return here, or you did it by putting everything to a chart here and getting the 16.4 by internal rate of return, or just did it like this and said here, calculate with the rate function on basics as long as you get there. But you had to calculate some returns on this, because ultimately what you need to find out is this intersection point. And that's when they keep talking about last two chapters, the incremental parts, and all the examples we went through had some form of incremental overlap. And the way to get that is basically takes the difference between the two. In this case, we did Y minus X, 185 minus 100 is 85. Or you can do it down here just as well, say that is that minus that. And so let me zoom into this section while I'm talking about it. So it makes it bigger. So you get rates of return. Now these are valuable, but this is the most valuable part because this tells you at this point in time, the two items, or the one that is most profitable, switches. They're equal at this point. So the lines in the graph we should talk about overlap. And again, this chapter really went into, the last one, trying to teach you about graphical representations. Well, over on that graph I showed a minute ago, the point at which they overlap is when you subtract the two values of X and Y, and that gives you that 8.59%. And if some of you will skip this point, you might have lost a couple of points, because if you went, some of you did like 0, 5, 10, 15, 20, 25, 30, and did it by fives on your rate table all the way down. And then you would say, okay, something switched between 5 and 10. Well, the answer isn't, they don't switch at 10%. They switch at 8.5. If you round it up to 9, okay, I could have accepted that if your calculations are right. But going from here to here and just simply saying, eliminating this line or anything between, no, the answer isn't 10%. At 5%, this is here. At 10%, this side is green. But the answer for the switch isn't 10%. Your whole percentage point off at least. So if you just did 0, 5, 10, and skip the idea of finding the intersection point, that can cost you points. I didn't really care if you put it in a formal thing like this. The book does something like this choice table where it says, okay, you pick Y when it's less than or equal 8.59, which is here. Then you pick X when it's greater than 8.59, which is here, up to do nothing after this point, because it's 16.4%. Y is negative, X is 0. So that's your break-even point. So that's where the ultimately nothing had, if you didn't graph anything after this, that was cool. But this is the point where you say everything's negative after that, and this is really the do nothing. You could, some people might argue philosophically, okay, could this be do nothing because it's zero profitability? Then you have to decide, well, at what point is minus $0.1 worth doing nothing versus 0? So I still put X because it was break even here. But there's any debate, you can philosophically just say, well, if it's 0, you're not losing money, you're not making money, so are you still doing X? And they put quotes around that at that point. This is the way the book would like it, but if you did something like this, but clearly highlighted where the switch points were, I would count that just as good as doing the choice table like the book does. Either one would get you there, but the key point was finding out your switchover points. And a lot of people just did this by 5s between 0 and 100, and if you did it by 5s without identifying that point, lost points on you're losing points on the homework. Any questions on that one? Either you're stupefied or you'll get it. So I'm hoping you'll get it. So then each one does the same type of thing, but gets a little more complicated. 812, we have 3 alternatives this time. And it can construct a choice table from 0 to 100, and then it asks you on part B, if you got a minimal accepted rate of return, what alternative would you select? Again, I did it multiple ways here, so I can sort of say, here they all are. I put the actual values in this table I'm highlighting here to calculate rates of return. Also, you could do it in just calculations by rates. Here I did B minus A to find intersection points. If you want to do a rate function by just taking the ends and the values like I did on part or problem 2, that would have been just fine. Whatever it took to get these, but at some point you're going to have to be able to subtract these from each other to find the intersection points, because you'll find B and A intersect here, B, C can intersect there, C and A intersect different point. Then I just graphed it or put it in a table over here. And again, at 5.74 where they overlap, you don't necessarily care about these two. So if you left this 5.74 level out, that's okay because B is the profitable one. But then somewhere between here, and again, if some people just still, they did their tables by 5s. And if you did it by 5s, you skip this number and this number and this number, which is the internal rate of return of B. But I just went through and graphed where the biggest numbers are in each column at each interest rate. The magic point is 6.22%. I got that by subtracting B from A, or A from B, I should say. Why did I do B from A first? Because B is bigger. Subtract the biggest one from the smallest one. Would have been wrong to do B minus C first? No, I did B minus A. But I ended up doing them all here. So that gets you, we okay, we went by 1%. 1%, you know, actually I could say if you went by 1%, you're gonna get there. And in a formal presentation, that would have been fine at 1% increments. Again, how big do you want your chart? I stopped really caring. If you really look down there, I did it by 5s after that, but the part where I know something's actually going on and the part I do in detail, that's my graphs a little skewed, they look logarithmic. But after 15%, it was always negative, so I didn't bother playing with this after that. Then I started saying, okay, if you're just going by 1s, you would have said something happens between 5 and 6. How do I find out what happens between 5 and 6? Well, I look at what was changing. And wow, between 5 and 6, A and C are doing something. It's irrelevant because B overwhelms them both, but they are. But I know that, oh, something between, if you did it by 1%, I notice that something between 6 and 7 is happening. Because at 6%, this is most profitable. 7%, that one, A is most profitable. So I know somewhere between 6 and 7, the profitability switches from project B to project A. And that's a hint where I might say, well, that happens, let's subtract B from A and find out where they exactly change. And at that magic 6.22%, A and B are equal. One smidgen below 6.22, B is profitable. One smidgen above 6.22, A is profitable. But that's the switch point. If you did 6 to 7 instead of switches then, okay, 6 would be one, 7 would be other. And this gets back to what I talk about doing these things in presentation format. Think about how you're trying to explain this to someone. That might be easier. So when it comes to these, and this is exactly what the book does in their examples, B minus A, all I did with here is take that number minus that number and did it all the way down. Now what that's going to tell you is it's honing in and giving you the internal rate of return of the difference, which is basically the same thing as telling you when these two things are the same. Sort of go back to basic algebra, if you will. By saying what the difference between these two are, I'm holding on to the difference and saying at this point they intersect. And that's the key point. And that gets you down to the graph. I'm not making it go by, but remember that B versus A. I got B and A. B is this orange, A is the blue. Well, they intersect right here, that 6.22. I include that in my graph. And that's what you do by subtracting one value, whether it be A from B, B from C, whatever it is. You're finding the subtracting two finds you the intersection point between the two options. Again, you don't always care about these intersection points as what, even though I put this 5.75 in here, or 5.74 in here, for example, but really we don't care about it because all we're concentrated is on B. But yeah, if you go down the graph, you'll see that C and A, C being the gray, A being blue, they actually intersect over here. Where is it? Oh no, over here, at that 5.74. Now we're not that concerned about that because B is above them both. But if they were overlapping more, but they do intersect at 5.74, then the other two intersect at 6.22. And those are basically how you know the intersection points and where the lines will cross on the graph. Now, if you don't graph it, by doing this, I can just stick that and do a rate calculation on it, and that'll tell me how things are changing. So in my case, I did both. I did a graph and I did a rate calculation on the exact numbers, because finding the overlap, it tells you where one switches from that instant where one switches from being profitable to the other being profitable, potentially. And that is the switch between that 6.22 is when it switches from B to A for profitability. Now, if you really want, I can, and this is where the question can be often, which would, if you really want to get down to which would you recommend, A or B? At this point in time, you're indifferent between the two. By convention, I usually call the one I started with the one that owns that 877. Is it wrong to say that point? No, but at this point they're equal because the lines are overlapping on the graph. Does that make sense to anybody? No one. Oh dear, it's a tough room. The whole thing is finding out where they equal each other. And to do that, you subtract one option from the other. Again, I tend to put the bigger one first, just so the signs turn out right. That's why I did B from A and B minus A and B minus C, because B was big. Then I chose C minus A. Why C minus A? Well, the cost of C is bigger than the cost of A, and that made the signs come out right. Will you get the same thing going A minus C? Yeah, but it kind of looks funny. And it's purely aesthetics. But A minus C is the same as C minus A. Just the signs the costs are flipped. Positive to negative, positive to negative. So I really didn't need both of these, but I put them there just to show you that, look, they're both the same. And it all comes down to this graph, which the book really pushes to say, look, here's where the value is. At certain interest rates, one is more profitable than the other, and it switches over time. Now, as I alluded to last week, can these ever, on some more complicated cost scenarios, cross again? The short answer is yes. Internal rates of return can have multiple values when you're dealing with some weird cost parameters. But for our purposes, I'm saying not worrying about that for now. Any more questions on 812 before we move on to 833, the really onerous one? Hearing none. Oh, go on. Last chance. All right, 833. This one is actually the same type of thing you've done before. They just give you, 5 or 6 scenarios depending how you count, sell, and keep. One of the biggest mistakes I've found so far on this one is people have forgotten that there is salvage value, and it's thrown your calculations off. There's like 2 or 3 of you forgot to add in salvage value on your cash flows. Now, so you could have done this multiple ways to find your rates of return. Again, you could have used the rate function like we did over in 8.2, just stuck in the values of N and payments and that. Or you could have done what I did and just graph the payments on a table, 0 through 15, and calculate that. Now, what this does in general too is tell you, internal rates of return, you can get away with this without doing them, but they do tell you certain things because you know that at a certain rate, after 11%, this one's no longer profitable by definition. If 11% is the internal rate of return, the break-even point for these cash flows, anything higher than 11%, you're not interested in those rates. So I did a couple of things. I also did some minus tables to find overlap points. 5 minus 3 means 5-story option minus 3-story option. 3 minus 1 is 3-story option minus 1-story option. And in one sense, I backed into them. When you say why I chose those ones, I backed into them actually. Because I did my graphing table. It says 1 through 100, but I noticed very quickly at 20%, they're all 0. So I didn't bother. If you stopped after they all started being 0, it won't be there. Salvage value is not 16. It is not stated. It's year 16. At the end of 15, we had this very conversation last week. Salvage value was stated to be at year 16. It was not. It happens at year 15, the way it has in every single example you worked in this class since day 1. There's no mention of year 16 anywhere in this question. If it had, then you would have had to put it year 16 and explain why you did nothing with it for a year and let it sit around before you sold it a year later. Salvage value is always in the end of the termination of the operations. You sell at the end of the year after reaping the benefits of it. We've done that without exception. Now then, so I did the same thing before. I did rates. I did 1 through 10, then 11, and I stuck in some extra ones. Say, where did I get extra ones from? I got them in here to see what things are changing. So I basically did net present value by rate and going 1 through 10. Why did I highlight this? Well, that's actually part B, which you're not asked to do. But I did it anyway. You only asked to do 833A. But it comes out, when you do it by rate, it comes out fairly quickly that, oh, look, this one is the biggest number up to around 8%. So they say, okay, well, somewhere in this section here, the profitability changes between 5 and 3. Because you can look here and say, look, all of a sudden, at here, 5 goes to 241, Here, 3 goes to 246. Here, they're equal. Now, the fact they're equal means you didn't have to do the calculation I did up here, 5 minus 3 to get 8%, because they're exactly equal, that and that. So that tells you right there, the intersection point is 8%. They're equal. So 8%, they match equal, and it's the switch point where one fraction over 8%, the profitability switches from five story to 3-story. At one fraction below 8%, profitability switches from 3-story back to the 5-story version. So that's when I know I have an overlap there. And when you graph it, in all this mess here, 5-story is dark blue, 3-story is light blue. You'll actually see at 8%, you can see on your shared screen, which is probably very tiny, they overlap right there. And that's the intersection point at 8%. And I just looked down my table and said, okay, that's really great. This goes down here, this goes down here. Then I suddenly noticed that something happened between 11 and 12%. The big number of net present value switched from 3-story to the 1-story. That told me there was something going on between 11 and 12. So that's when I decided to do the 3-story minus the 1-story to find the exact spot which they change. And so that's why I have 11.4% here, because I've just stuck it up there and said, well, 11.4% is that overlap. And sure enough, when you put 11.4% and say, what's the net present value? 1 and 3 story options are the same. And if you look at your graph where I graphed it, 11.4%, 3 and 1, it's hard to see in this mess of lines, but 3-story and 1-story, that's 11.4 are like right there where they overlap. Again, and this is where I would say, if I was presenting all 5 options in a formal presentation, I think this table works better than this graph, because everyone's going to be sitting at the back of the room where the CEO usually sits at the head of the table. He's going to stare at that and say, where do the lines cross? So in this particular case, on something with this many options, I actually prefer a table like this, because then you can say, look, here's the switchover point. And then you can go all the way down, since you're now here. Well, by the time you get down to 13.3%, which is the internal rate of return of the 3-story building, everything's negative except for the 1-story option that you're already on. Well, the 1-story option goes to 0 at its internal rate of return of 15%. So that's the point where after that level, nothing's profitable, because 15% is the highest internal rate of return. So that's essentially, these are the 3 areas of profitability for what you've got to do. So if you did a chart like this and highlighted it, that'd be fine. If you did a formal thing like the book does, and like to say, here's a choice table, here's what I did. I said, basically, if it's less than or equal to 8%, the 5-story option, that's this highlighted green area, less than 8%. Well, if it's greater than or equal to, or should less than or equal to 18.4, meaning between 8% and 18.4%, that's where this highlighted green becomes profitable. Then you get less, that goes up until you switch to the 1-story. Whoops, I forgot to put my 1-story in there. I'm missing a 1-story. But you have a 1-story option in here as well, which takes you from that 11.4 to 15%. Because that switches over there at 11.4%. So this is, if this is greater than, equal to that. Oops. Come on. There you go. So you have 5 stories, then 3 stories, then 1 story, and then nothing at all. And that's the formal choice table. But if you did something like this, that's acceptable. If you did the graph, I would take that. The main thing with the choice table is giving what your choices are, your optimal choices are, and where people lost points on this, like I said on the earlier, I had people do some really nice calculations like this and didn't indicate anything about what they thought the profitable period was. Going to ask you to construct a table. Well, construct a choice table means where the choices are. Well, this choice table tells you, hey, these rates do this. If you just constructed this, it give you data, but it doesn't give you you're not answering the question. And the choice table says, okay, what's the choice at these rate levels? Highlighting this in green at the same levels that this little box works gets you there. So if you didn't say anything about it, but just put a bunch of data up there without any indications of where you should be going, you lost points for that, or you will lose points for that. Any questions on this one? It's a lot of stuff, but essentially it's the same as the first two problems. Just we've gone from 2 choices to 3 choices to 1, 2, 3, 4, 5, 6, 7 choices. You're doing the same thing every time. So either dumbfounded or you all get this. You'll have no problem with this on the quiz. Okay, I'm hearing none, so I'm about to say goodbye to this, and I'll go to the exciting PowerPoints. All right, I'll save it. Now then, oops, did that. Other analysis techniques. Cool. This is where we get into other ways of looking at things, and one of the most common ones out there. Now then, example 9.1 starts off with something that sounds, and this is kind of, if you haven't been inundated like don't smoke ads, one of the favorite things is to show you, hey, if you didn't smoke cigarettes, you would have saved umpteen gajillion dollars by your 65th birthday and lived longer and happier. This is the sort of how much would you save over your lifetime if you didn't buy cigarettes type of question. They phrase it in, okay, you have a smoking habit. What is this annual savings you're going to pay? You're paying $35 a week, which nowadays in Oregon, that's pretty cheap for cigarettes. That's like 4 packs, I think, at most. Cigarettes are expensive. So what is the annual savings if you quit your smoking habit and you're going to keep going, not smoke for, 40 years or 45 years at age 65? 65 minus 20. $35 a week you're spending. And you can do semi-annual compounding. Again, some of you are still on your homeworks or messing up when you have semi-annual. Remember, that's twice a year. So when it's twice a year, well, you can't buy them. You have to be 21 to buy cigarettes now? Wow. So you have to be able to drink and buy cigarettes at the same time. That's double whammy. That's hitting youth fast. Okay. Well, so 35 times 26. Why? Well, you think about weekly smoking habits. Okay, semi-annual savings times 26 is $910. So 2 ways to do it. You can do your future worth and your ratings to come up with 2.5%. Why 2.5%? Semi-annual, so you cut the 5% in half. Why is it 90? Because when you cut this in half, it's because you're doubling the periods of compounding. 45 times 2 is 90. So that's why if you do the rate method, you go to that page at 2.5%, look at the column 90, that gets you that. If you do it in Excel, 2.5%, end periods, payment rate, present value, future value is what you're generating here. And so basically, if you stop smoking for 45 years, assuming it was only costing you $35 a week, you'd have an extra $300,000 at age 65. Cool. Nothing we haven't done before. Now let's get part two. Now then, a work week habit costs $7 a day. That's like a grande latte. If $2 a day alternative is substituted, basically, how much do you save? Okay, the calculations on this is not a new type of problem, but we're leading up to some new types of problems. So $5 saved on 4 days is $20 a week. $500 every 6 months. Just doing the arithmetic. So by switching off that habit from $7 a day to $2 a day, okay, maybe you get bottled water instead of a latte. All right, well, that tells you you're going to save $171,000. Starts to add up. Okay, again, this shouldn't be something new, but we're working your way up to something to get you thinking about these types of things. You with me so far? This concept we're doing, we're basically taking annuity payments and figuring out the future worth. So think about the annuity chapter, which was what, chapter 6, I think, if you're not sure how we're doing this. But the habits are all even amounts coming steadily over a period. Now then, got those calculations. Now we're going to hit you to something that we haven't talked about a great deal. We touched on this a bit. Benefit cost ratio. And this is a technique used out there in the real world a lot. And basically say when you're doing the net present value of the benefits minus the present value of the costs, if they're greater than 0, well, cool. That means benefits are bigger than costs. So you take whatever it takes to make those equivalent. So the equivalent annual worth is equal to equivalent annual benefit on equivalent annual cost. And if that's bigger than 0, we do it. Those are review things. We should remember that. We've done that before in saying, should we do the project? And you figured out the equivalent annual costs and equivalent annual benefits. Now we talk about this in terms of ratio. And this is a way we can compare multiple projects to each other in a new manner, because we've been doing net present value, we've been doing internal rates of return a lot, other types of things, equivalent annual worth. Now I can say, okay, how much do the benefits outweigh the costs? And they give you this nice little, what we call a well-done element, saying that, well, if the benefits are bigger than the costs, that means it's going to be greater than or equal to 1. Because the costs, if the numerator is bigger than the denominator, this ratio here, the equivalent unit of benefits, the equivalent unit of costs, are going to be greater than 1 because the top is bigger than the bottom. That's where we're going with this ratio. I'm going to start doing equivalent annual costs. So we jump to 9.3, and they're giving us, a similar type of calculation that we've seen before. Okay. Device A, we have an annuity. These are both 5-year periods. We're paying out $10,000 and getting $3,000 a year for 5 years. Device B, we've got $13,500 out the door today, and we're getting a wonderful gradient function because the author of this book really loves gradients, and he's always trying to find an excuse to use a gradient calculation. And he says, okay, in this case, for 5 years, we're spending a little bit more up front, but we get $3,000, then $3,500, then $4,000, then $500, then $5,000. Going up by $500 a year, it's a gradient. So he does calculations here. Well, we need the present value of a 5-year annuity, present value of the annuity. The annuity is $3,000. It's 7%. Why 7%? Because they told us that in the example. 5 years. That gives us, by multiplying 3,000 times that factor in the back of the book, 12,300 over the present cost. So this 12,300 is the present value of that 5-year annuity. Again, this is old math. We've done this before. Well, then you take the ratio of those two, the present value of all the income we're going to get in the future, divide the present value of the cost, because we're at year 0 right now. That gives us 1.23 as the ratio of benefits to costs. Same thing here. We have a gradient function instead We have 13,500. 3,000 present value of the gradient of this present value of these cash flows is that over that. We'll do it my way next. Here's how I did it. I think this is a little cleaner. 7%. Here's the cash flows. Present value of those cash flows using net present value, 12,301. Present value of these cash flows is 16,124. Remember, this is the cash flows here. I didn't say net present value, I'm not netting anything. Present value of this 5-year annuity, present value of this. Costs, they're already in present value because they were given to us here. What we didn't have in present value were the future payments. Take 1.2301 or 12.301 divided by 10,000, 1.23, 1.19. From a standpoint of how do the benefits stack up to the costs? Well, device A looks better. How do you know it looks better? Because 1.23 is bigger than 1.19. Now then, just for clicks and giggles, example doesn't do this, but I always like to throw in net present value and IRR to the book's examples, because if I've been hammering you at one thing after another, is that these types of ratios, whether it be benefit cost, net present value, or internal rate of return, by themselves are just aching to give you false information. And I love to show this because the benefit cost ratio shows device A is best. Net present value says no, device B is best. But then no, internal rate of return says no, device A is best. So which do you choose? Anyone want to venture, go out on a limb? Which would you choose? You got contradictory data here in your analysis. No one wants to go out on a limb. Well, that's smart, because
I like net present value.
Man after my own heart. No, actually, of all these things, I still always go back to net present value. But even that is flawed, because if cash flow is an issue, well, you know, how much uneven payments do that? But of all these, I think net present value is the soundest, but even it's not without flaws. That's why I always say, looking at just one stat, you're asking me trouble. But I agree, I like net present value. Of all these, I like internal rate of return the least. But benefit cost ratio doesn't tell you anything about the cash flow you're getting in. And sometimes you just need to stare at it and say, wow, which is more valuable to me? $3,000 every year, that's predictable. An accountant would say, I like $3,000 a year because I can budget off of it. I don't have to do any extrapolations. Finance person might say, well, what's more important to me, $5,000 in 5 years or $3,000 in 5 years? It's easy to budget off device A's cash flow. It's harder to budget off device B. But again, the book doesn't put these in there, but it's just always keep in the back of your mind that, you know, okay. Payback period. Done this one so many times, and it's out there. People love it because again, it's a bit like internal rate of return. It's simple. Is it flawed? Yes, all these methods are flawed. That's why you learn more than one, and have to evaluate which one is true is the hard part. So they can all be true and they can all be wrong. Payback period. This is basically the time required for projects' profit and benefits to equal costs. How much time, how many years, how many of those ends in our cash flow does it take to pay back what you got? So, you got a question, Jake, or did I missed your hand up? Okay, just here. Make sure I didn't miss that one. So, basically what this is doing, and it's basically an arithmetic test, is saying how much, when do I get my money back from what I'm spending? So, payback period. This is one that's used ad nauseum. Two different cash flows, A and B. Now we know all about calculating net present value, internal rate of return on these, but they're saying, okay, how fast do I get my money back? So you got $1,000 here, and how long do you have to go until these cash flows have zeroed out the amount you spent at the beginning. Well, book has their little way of showing it, and I did it this way. In year one, you pay $200, or you get $200 back. Well, in that case, so you get $200, that means you got 1 year and you got another $800 to keep paying off. That's this amount left. Because it's $1,000 owed, you get $200 the first year, you still owe essentially $800. Well, next year, what's your cash flow? Year two cash flow is this year two, $200. Cool. Well, now you paid a total of $400 back against that $1,000. You owe $600 now to pay off that $1,000. Well, in year three, okay, the total cash flow is $1,200, but you only need $600 of it to pay off the remaining balance of $600 that was left over after last year's payment. Well, so then at year three, you use $600 to get up to that $1,000 you paid back. Now you have nothing left of that original $1,000. So that's where you have this 1 + 1 + 600 over 1,200. That first one is the year one, $200. Second one is the year two, $200, plus the 600 divided by 1,200, because you only needed half the year to pay it off, because you used only half the money that came in that year. So that tells you you paid it off in 2.5 years. Now that seems simple up front, but the simple calculation has destroyed higher paid people than me. Is anyone with me so far on that one? No one. Okay. So we got to think. We're talking about payback periods. We got to get how long is it going to take us to pay off the original $1,000 investment? And if you notice, so far there's no interest involved. We're just doing straight payback. We'll get to interest. But how many of these payments does it take to pay off $1,000? Well, 200. The first year of 200 is less than 1,000. So at the end of year one, we pay off $200 because that's the money we get in. We still have $800 left of that original 1,000. The next year, we pay off another $200 against that $1,000. Cool. That leaves us 600 because 1,000 minus 400 is 600. In year three, we get another infusion of cash flow that we can use to pay off that original $1,000. We've already paid off 400 of it, 200 there, 200 there. You have 600 more to go of that $1,000. Okay. Well, we're going to get a total of $1,200 through year three. We only need half of it. So half of the 1,200, which is 600, which is what we need to pay off the rest of that $1,000. Half of that is 600. The whole is 1,200. So we say, all right, we only need 600 out of 1,200, which is 0.5. So the payoff period is 2.5. 2 years, year one, year two, and half of year three was necessary to pay off that initial amount. We do something similar, and the math is a little easier when you have annuities, but we'll do it the same way. We have $2,783 to pay off. Well, at year one, we get $1,200 in the door. We get $1,200, and after that, we pay off the $1,200. 2,783 minus 1,200 is 1,583. So at the end of year one, we've paid off $1,200, but we still owe another $1,583. Well, next year, we're not getting $1,583, but we're getting another $1,200, because it says right here at year two, $1,200 on B. All right, well, we're paying off another $1,200 towards that leftover $1,583 on our way to paying off the whole $2,783. Well, okay, if we take $1,200 and apply it to the leftover $1,583 we still owe, we have $383 left. Well, we're out of money for our cash flow this year, so we're gonna have to wait till year 3. So you know it's gonna be at least 2 years and some change to pay off, before we paid off time-wise the full loan. Well, year 3 comes along. We get another $1,200 in money. We don't need all of it to pay off the remaining $383. We only need $383 of that $1,200. So that means we have year 1's payment, year 2 payment in this 1 + 1, just like we did above. But now we only need $383 of the $1,200 we had. Well, 383 divided by 1,200 is 0.32. So the payback period is 2.32 for B compared to 2.5 for A. And the one that throws people off is the final year calculations, usually. But now we have an idea, and this is where I've been talking a lot about cash flow, where net present value, internal rate of return, and the cost benefit ratio don't take into account cash flows. Now we're starting to take into account how fast money comes in from our project. Because we're saying we can pay project A back in 2.5 years, or project B back in 2.32 years. Well, depending how cash strapped you are, you might be more concerned about paying back faster than getting a higher rate of return on your net present value or internal rate of return or cost benefit ratio. Because we're going to have our full money paid back on this project, you know, maybe difference between 5 and 0.32. You know, that's a whole calendar quarter sooner, if you will, 3/12. Is anybody with me? Because it's an easy thing to talk about, but it gets tricky. So I'm now going to make it really tricky. And I'm actually combining this example with a later example, because payback period is what people like to do. What they should do is called discounted payback period. Because as we know, $1,200, 3 years from now is not the same as $1,200 today. That $1,200 in 3 years is going to be worth less than it is $1,200 today. And so we have something called discounted payback. And this is where you do the exact same calculations, except instead of starting with our original table, which is up here in the upper left, that's the same one we used to get original paybacks. We then say, okay, we need to know what the present value, because the dollars we're paying out are in present value dollars. We need to know everything else in present value dollars, so we can say what the real payback period is going to be, because the dollars we get paid back in the future are worse than the dollars that are being paid today. Because we learned time is money, and the farther out you get your check, the less that money is worth. So I take these periods over here, the 200, 200, 1,200, 1,200, 1,200, and the 1,200, 1,200, 1,200, 1,200 annuity, and I present value them. All I did is take 8%, why? Because they told us that, and said, okay, at $200 today at 8% that we're going to get a year from now, because right now we're making a decision, we're at year 0. The $200 we're going to get end of next year is actually only worth $185 in today's dollars. Remember, we're discounting this back. What does that $200 equal today? It only equals 185 in today's dollars. So that $200 2 years from now, it's only worth 171 in today's dollars. And so on down the line. So you see, it gets less and less. Similarly on part B, that $1,200 they're going to give us in a year, well, that's only worth 1111 in today's dollars at a discount of 8%. And you do that to every single one. And I can show you, if you want to know the Excel, whoops. Here's what I did in my Excel. All I did for here, I can't make the equation get big, but in order to get this, I did a present value calculation of 8% and that against $200, that $200, and present valued it. Let's click up here so we can see it. $200 at 8% for 1 year. Next one I did $200 at 8% for 2 years to get this. On the final one here, I did that K4 in my formula here. My J11 is 5 periods. So the value of the $1,200 that I'm going to get in year 5 is actually only worth $817 today, meaning at year 0. So what I'm doing is taking all these future payments and saying, what is the equivalent value at time 0? I'm present valuing each one of these, one at a time. Now then, going back to here, that's all I've done here is taking the present value at year 0 of each one of these, year 5, discounting back 5 years at 8%. So find the present value of each one of these. A's present value, cash flow. 0 doesn't change, time period 0, because we're already in 0. There's nothing to discount. So this time I do the exact same calculations I did before, except instead of before I had $200, now I'm going to use the present valued $200 or $185. So at year 1, I get $185 of that $1,000 paid off, which leaves me another $815 to go. At year 2, well, I have $171 is the present value of the 200. 171 applied against the 815. Okay, I have $644 left. Then, well, at year 3, I'm getting another $953. Well, I have an outstanding balance of $644 and $953. I only need $644 of it left. So it becomes, I take $953 minus $644. Well, it's 644 divided by 953 is 0.68. So it was before when I did 1 plus 1 plus 600 over 1200. This time I'm doing 1 plus 1 plus 644 over 953. Because that's what the payment is. I don't have nice $1,200 even payments anymore. I have discounted amounts. And that means, so 644 divided by that 953 gives me the 0.68, give me a 2.68 payback period. I'm doing the exact same math I did before, except I've gone from absolute values here on this A and B part to present value dollars in the A and B part. And you'll see the time period to payback takes longer. Part A, which we did on the previous page or previous slide, was 2.5 years. When I discount the payments in the future into today's dollars, the discounted payback period goes up because values go down over time. So discounted paybacks take longer than non-discounted. Now this is an important concept because a number of times I've been in here where we're trying to sell projects and why I convince people they should invest in our numbers. Most managers, if they're presenting their values and say, look, we're gonna get paid back really soon. Oops, Alex is back. They don't like using discounted payback because it's not as nice looking. Discounted paybacks take longer. So when I've done this in the real world, I do both because I know more, if I know who I'm up against on, it's my project versus someone else's project, they're going to make themselves look as nice as possible. So I show both. And if I show both and my opponent, if you will, that I'm competing for budgetary dollars with, doesn't, not only do I show that I'm looking like I know more, I'm making him look like he's hiding something. So this discounted payback is an important concept because it shows you know what's what. You're acknowledging the time value of money. And if the other guy doesn't do it, cool, you've made yourself look brilliant in the conference room. And they'll trust you more next time compared to the other person you're up against. And it happens all the time. It is so common for people to say, hey, look what they're doing. Now again, I also, just for clicks and giggles, I put down here and I calculated internal rate of return on A and B to give you an idea that, okay, A has a 49% B. So A wins by net internal rate of return. Net present value is about the same. A has a longer discount payback period. So which do you want to do? Net present value is a wash. One has a higher rate of return. One has but then they have a higher payback period. Again, I did this to show you that, again, by themselves, as I said, ad nauseum. Oh, I misspelled discounted. I counted. Isn't that kind of Monte Cristo? Anyway, so anyone following me? Is anyone following this? What I did here? You're doing the calculations for payback the same. You're just discounting the cash flows compared to what we did in the first part of the example. But payback period is a very, very common thing. You need to understand it, not just for this class, but out in the real world. Banks love to see this on bank loans for projects. Budget people like to see it all the time. How fast are we going to make our money back on whatever you're doing? How fast before we break even on our project? So we've done it with interest rates, we've done it with net present values. Now we're saying with time, how fast are we're going to get paid back? And that's the important thing on this one. Any questions on that? Oh, sure. Let me pull it over. So on here, present value, all I did here is, I know again, can never make the formula bar bigger, but let me clear my throat. We'll click on one in the middle. All I did is say here, interest rate is locked down as K4. That's up here, the 8%. The number of periods I'm discounting back is this J9, which is this J9 is 3. Why am I discounting 3 periods back? Because I'm in year 3. And F8 is, what am I discounting back? Well, I'm discounting this $1,200 back 3 years at 8%. That turns this $1,200 in year 3 into $953, because that is the present value, meaning the value at year 0. That's turning $1,200 into $953, which is the value of that $1,200 at time period 0. So we can say the payback dollars are the same value caliber as the initial investment. We paid out at $1,000 at year 0. What we're paying back with should be the same value of year 0 dollars. But we know $1,200 in 3 years is worth less than $1,200 in today's dollars, because money out in the future is worth less in today's dollars. Did that help? And again, the same thing for all the others too. All I did is just say here. Let's see if I can get the, let's see if the formula will show up. Show it better. Ah, here, that may help. But if you can see, I'll put it down here. The rate on this, for this formula for A, the rate is K4 up there. Number of periods is 3 periods, that J9. The future value is the $1,200 that we're going to get paid. And that gets, oops, lost Antonio. So that's all I do. Each year is one at a time being discounted back, so that when we're doing discounted payback, everything is in today's dollars. And that's the whole goal. So we're saying we're paying this back in today's dollars. It is avoided by people who don't want to make their projects look better, because let's face it, 2.5 year period or 2 3/4 period to pay back. Well, I want to say it's 2.5, not 2 3/4. Well, if they're smart, they use discounted payback. Again, I always put both, because if one guy's doing non-discounted, I'm going to say, here's my equivalent way of his doing it. And I say, here's how you should do it. And if he hasn't done it, he looks bad. Sensitivity and break-even analysis. Oh, 408, we're cooking with gas. So we've already been doing this. We just haven't talked about it in these terms. So basically, how much do things change in order to say whether or not we do something or not do something? How sensitive is it to change? Now, we've already been doing that in the past chapter 8 with these, how much do we change the interest rate before one project stops being profitable and another one does? That is a form of sensitivity analysis. So we're already doing it, but we're going to do a little bit more depth into it and say, okay, when are two things going to be equal to each other in different time frames? We've already been doing this. So here's what the book does. They give you 2 ways of constructing stuff. We've had an example like this before. And you say, all right, we can either build something today at the full capacity we can need forever, and it's going to cost us $140,000 to do it. Example, what, 910 on, where the heck are we? We're like page 319, I think. Yes. I'm going to take a couple different ways of doing this. Well, we can spend today, in today's dollars, $140,000 to build what we're going to need that's going to last us forever. Doesn't mean we're going to use it all, but we can build it now for this much money. Or we can do $100,000 today, and then at some period in the future, it's going to cost us another $120,000. Question is, when in the future is that viable to do? Because we're going to have to make a decision, say, okay, we think by today we can do another $120,000 sometime in the future, but when is it going to be viable to do that? When does it stop being valuable to that future payment? That's essentially what they're trying to do. So what they do here is say, okay, when will the present value of the full capacity, the $140,000 today, equal the equivalent of doing the $100,000 now plus $120,000 sometime in the future? And the key is we don't know what the sometime in the future is, but we're going to evaluate when it can be viably, so we can say whether it will work or not. And this is like a first step in a larger problem. Well, we can do it the old-fashioned way, and we just say present value of doing the full option now is $140,000. We know that because they gave us in this nice table, and they're going to say, when does that equal $100,000, which is today's value? Why? Because this is $100,000 now, plus 120,000 times some present value of a future value at 8%. Why 8%? Because they told us 8%. At some end period in the future. And so we can say, well, we know everything except this factor, but we have a page that's labeled 8%. Cool. Well, we take 100,000, do the solve for this interest factor here. That's in the back of the book somewhere. And we say, okay, take $100,000 over there, makes it 40. And $40,000 divided by $120,000 is 0.3333 or 1/3. And we go to our present value interest factor page on the back of the book at 8% and see if they actually have one. Because we want to know the present value of a future value, meaning what is the present value of that $120,000. So we need to find a factor at 8% that's equal to 0.3. So we look at the back of our table here at our P/Fs and say, okay, where does something equal 0.3? Well, unfortunately, they don't have an exact number for 0.3333. But there's not going to be somewhere between 14 and 15%. And I'm looking at the page 643. But rather than have you do that, let's go to my Excel version. Okay, and we do our usual stuff. We have some full capacity, 2-stage, delta. Well, what we're doing is going over to my 9.10. So we have an 8%, and we have at 0, we have $140,000 and $100,000 being paid today. They told us that. Sometime in the future, and we don't know what that is, we're gonna have to pay $120,000. Cool. Well, and we need to know when they equal each other. This is very similar to last week's homework. When are we finding out the overlap on these things? When do these two equal each other? When does the paying all the money up front now equal paying 2 stages? Well, just so happens we have an Excel formula for that. We know 8% because it is our discount rate. We know that the present value of our amount is $40,000. And basically taking the two items we have, the full capacity and 2-stage, and taking the difference, just like we did in everything else in this past week's homework. So we have $40,000 difference between these two. We're trying to find out where they're equal. We're trying to equal these two together, just like we did on the math and then Excel just a minute ago. Okay, so that's where we get in our usual little format here, a present value of $40,000. We know that in the future, we're going to have to spend another $120,000. We don't know how far in the future, but we know that at some point in time, spending an extra $40,000 today is going to be the equivalent of spending $120,000 in the future. Now then, this is the part where people say, huh. If anyone wants to say, huh, feel free. But think about it. By spending $140,000 today, we're not having to spend $120,000 in the future. What does it cost us to not pay that $120,000 in the future? It costs us the extra $40,000 above the other option, which will make us pay $120,000 in the future. By paying $140,000, the full capacity today, we don't have to spend that second $120,000 some point in the future. And so that's where we get, and this is the tricky part, all right, if we spend only $100,000 today, we have to spend another $120,000 in the future. In order to not spend that $120,000 in the future, we have to spend that extra $40,000 now. So the equivalent of spending extra $40,000 today, this present value figure, is going to save us that $120,000 in the future. So we just have this formula, which is something we haven't seen before, but you have a formula out there called number of periods. This gives you the time factor that you didn't have before. You have a discount rate, which they gave you at 8%. Payment is 0. There's no annuity here. And the present value, which is $40,000. A future value of $120,000. Because by spending $40,000 today, we don't have to spend $120,000 in the future. And they have n per number of periods, and that gives us 14.27. So what I did here then is I simply said, okay, here's our time. We're spending $120,000 a year. At 14.2 years, we have the present value equal at 14.2 years, 14.27 years, or when the value of these two are equal. And here's where it's tricky. Full capacity today, we're spending $140,000, today's dollars. We'll always, in today's dollars, we're always spending $140,000. That's today's dollars. And that's where the graph sometime might come to play. I'm going to zoom in on the graph. Because the problem here we're dealing with is concept. This line going all the way across is the present value of that $140,000 for option A in today's dollars forever, because you only spend it once. So the present value of $140,000 today is still $140,000 30 years from now, because we're not spending it in the future, we're spending it today. So we're saying over a time frame of 30 years, what's the present value of that $140,000? Well, it's always $140,000 because we're not spending any more money. We spent it today. It's in today's dollars. So this solid blue line is at $140,000 here, which is the present value. And these are all present values. Here is present value today, $140,000. It's going to have a present value in 30 years of $140,000 because they're only spending it today. Now then, the two-stage says, okay, the present value of $120,000 today, which is, where's my formula? I don't want that. Why don't you give me the formula? Oh, it won't give me it because I have a plus in here. So what I'm doing here is saying, okay, a two-stage is actually going to cost us ultimately $220,000. So I can spend on two-stage, I can spend $220,000 today if I want to build the whole thing into 2 stages within 1 year. But I discount that back every year because if I'm going to spend that money 5 years from now, it's worth less. And the one time that they're equal is at 14.27 years. So what this is telling me, and this is tricky, but the math is nothing you haven't done before in formulas, except for that one new number period equation. But what it's telling you here, philosophically, is to say, well, up to 14.2 years, I can build this and I'll be okay. I can do 2 stages because up until this point, it's worthwhile building. But after this, the value gets less, less, and less. Meaning, if you want to pick options, well, this tells you if you can't build it the second half of the building, but within 14.27 years, you shouldn't try that option. You should do the first option of building it all at once. Because if it takes you longer, then it's just not getting value for it, essentially. And that's why we see this line going down over time for cost-wise. Because by discounting the amount of money here, it tells you when, gives you an idea about when you can build it. So the break-even point is that 14.27 years where you don't care about the two options. Each one's done. Then it just comes down to time, being able to say, well, do I think I'm going to have to build it before year 20, or am I going to have to build it by year 10? This tells you when you're indifferent about the two projects. But now you have to look at your manufacturing manager and say, hey, how long can we go without building the second stage? How soon do we need it? There's a lot of silence on this one, but I think it's a complicated example. Too much silence on this. I'm not sure if I should move on or flog this horse some more. But it's a critical example of understanding the deltas. Coming up with this $40,000, and it all comes down to this formula here and the number period. Because you got to say incrementally, I'm spending an extra $40,000 here. Oh, the function is N per, standing for number of periods, NPER. And I'll click on it here. And basically, it gives you all the things you're used to seeing. An interest rate, payments. In this case, you don't have payments because you're not paying for anything between the starting point and the ending point. You have, so payment zero, I could have left this zero. Present value is $40,000. That's the additional money you would have to spend to not spend the $120,000 in the future. You can spend an extra $40,000 today. In exchange for that, you don't have to spend $120,000 in the future. But if you do the two-stage option, you got to spend $100,000 today and then another $120,000 sometimes in the future. How far in the future, you don't know, but this basically gives you an idea of saying, all right, I got a break-even point called 14.27 years. And then you can say, then you look at step 2 and say, all right, when do I have to build it? Can I build it at year 5 or year 5? If you're going to build it in 5 years, well, sorry, it's going to cost you more than doing the full thing. So that's when you look at this stage and say, well, when is it worth buying? If I have to build it in year 5, someone keeps trying to call me. They won't take no for an answer. So that's where we get a number of periods to find that magic place when you know that you got to have some period of time when this is going to break even for itself. This is how you calculate, when you know everything but time, this is how to find the time. Any more questions before I move on? Okay. What if, for multiple, when you can change multiple variables? I'm just going to stick this one quickly. Those 3 examples I went are the main gist of what I want you to know. But 913 is one that I really think they should have had the very first week and say, what if scenarios? And basically this is, in my opinion, how to design your spreadsheet thing. What if analysis when you can change multiple variables? And all it does is say, okay, in the real world, and this is very important because being able to change your spreadsheets on the fly during a presentation makes you look so cool when you've got your PowerPoints up there and you suddenly put up a spreadsheet. Because if you have a PowerPoint up there with the numbers up there, there's always some twit in the back of the room that says, yeah, but what if it costs us an extra $5,000 to buy that machine? Well, you have a dynamic spreadsheet you can set up and just quickly change it. That's what's cool. And quite frankly, one of the reasons I can adapt so fast to these changes in books examples, unless they change the problems really well. You know, one of the guys I talked about in this textbook, where he likes to change the problems by having the exact same problems, but just changing one figure. everything I do is changed up so I can change something automatically. This number will feed automatically depending on what I change, or this number will feed automatically depending on what I change in these. I can change the interest rate here, and it will change everything dynamically. And that's what they're trying to get to in this final example. And it's really, if you've been doing this all year long, your life is easier. Here's my spreadsheet. All I do is, and it's basically trying to say, hey, and if you're not doing it by now, you're probably not going to change for the 1 week left. But it's a good lesson, this 9.13 on how to set up your spreadsheets. And basically, it's sort of why I start at the very beginning when I say I have certain things I have in yellow, those things I don't. So if I have a question like this and I want to change it on the fly because someone during the presentation asked me about it, it's so cool. And I can just say, okay, instead of 10%, 15%, and everything changes out. Oh, okay, 15%. What if, oh no, what if it costs, what if, revenue goes up, goes up 5%. Instead of that, it changes everything. The whole part of this last example is, again, I wish we had it earlier in the book, is when you think about designing your spreadsheets, and I see this on the homework a lot, you set up your problems so it can only ever be used once. And I actually have templates for homework problems where I can just copy in if I get a new homework problem, and I start to use these. Where is it? I started to use these ones. I have templates all over the place for different things. I can copy and paste them. The whole point of this 9.13, I'm not going to spend a lot more time on it, is just to go through that. As you set up spreadsheets, what if analysis comes up all the time in presentations and when you're just talking to colleagues. When you're dealing with these things of payback periods, or what happens if you just change your time? What happens if this goes from 200 to 400? Everything changes dynamically. And it's just a little mini spreadsheet lessons on good practices. No, so I'm not gonna spend a lot of time on that, but it's worth reading that example. And it's basically just saying, hey, if you do this, things can change dynamically. And what's really cool is your graphs, if your graphs link into it, they'll change dynamically with it. Enough said on that one. I won't save because I can't remember why I need to save it. Alrighty, so let's take a 10-minute break. And if we're lucky, we can be out of here by 5. I got 4:29 or 4:30. Let's see back everyone at 4:40, get everyone enough time to get a drink, go to the bathroom and everything. Anyone want more than 10 minutes? Hearing no objections, I'll see you back in 10 minutes.
Imagine getting the best of the farmer's market delivered right to your doorstep. That's exactly what you get with full service.
Bye.